So looking at nearly an almost subcategory of our rates of change here, displacement, velocity, and acceleration. So in terms of what we're looking at, displacement generally uses the letter S, and it's kind of related to distance. And I've laid it out here, displacement is distance, but it's relative to a particular point. And that's going to be the same for the velocity when we look at that as well. It's all relative to a particular point. So we can see here just a simple example I just threw down. If John went 4 meters forward, he would have a displacement of +4 because he's 4 meters forward or to the right of the point where he started. Jenny going 6 meters back, she has gone -6 because she has moved to the left of the point where she started. So here displacement can be positive and negative, whereas distance is always positive. So that's the slight difference, I suppose, between distance and displacement. It's also worth noting that displacement, because it's distance relative to a point, if I go up and if I go forward and I go back, I haven't traveled a displacement of 8 meters. My displacement is back to 0. I might have traveled a distance of 8 meters, but I'm always just talking about where am I relative to that point. So if I was John and I went back now to here, John has a displacement of 3. Okay, because he's now 3 meters from the point where he started. Velocity then is speed relative to a particular point. So velocity is speed relative to that point. So kind of different. Speed is absolute value. Velocity again could be positive or negative. If we're moving forwards, our velocity is positive. If we're moving backwards, our velocity is negative. Noting as well, if something is said to be at rest, then that means that its velocity is 0, or the derivative of displacement would be 0. Okay, noting as well there, as I said, velocity and displacement are related through differentiation. Okay, I kind of skipped over this at the start. So velocity here, or displacement, we start with as S, and if we differentiate that, the rate of change, the rate at which my displacement is changing with respect to time, is my velocity or my speed. If I start with my velocity then, and I differentiate that, the rate at which that is changing with respect to time is going to be my acceleration. Okay, so we can relate displacement, velocity, and acceleration through our differentiation there. And it's very important that you have that relationship in your head at all times with these questions. So rate of change of velocity with respect to time is acceleration then. So looking at an example here, a ball is thrown straight up into the air. The height of the ball is given. Okay, so the height of the ball is given there. And we are asked now to find the height of the ball after 1 second. So let's do that. We're just subbing in 1 for t there. Fairly straightforward. So 10t, 10 times 1 minus 1 squared. So that's 3 plus 10 minus 1, which is just going to be 12 meters. Okay, so after 1 second, it's 12 meters high. Explain why this represents the speed of the ball and find the first derivative. So it represents the speed of the ball because we can think of it as being dsdt. So it's the rate of change. So it's the rate at which distance changes, or displacement I should say. Displacement changes with respect to time. And that is equal to speed. Okay, that is equal to speed or velocity here. That is equal to speed or velocity. Okay, to find that first derivative, we're just going to differentiate our displacement function there. What is the speed of the ball when it reaches maximum height? Well, maximum height means that my first derivative is equal to 0, and my second derivative there would be negative. So we can use both of those to just double check our answer. So let's find our first derivative and set it equal to 0 then. So that's 10 minus 2t equal to 0, which means that t is 5. I'm getting my second derivative there then. I get minus 2, which is less than 0, which just proves then that it's a maximum. So after 5 seconds, the ball will have reached a maximum height. Okay, or after 5 seconds, yeah, the ball will reach maximum height, because remember we're finding we're maximizing height, and we know as well that at a maximum there my speed will be 0 at rest. Okay, the speed will be at 0. I think I've answered the second part there, first of all. Okay, so this is really part V, I suppose. If we touch on part 3 a little bit more, so let's just talk about that in a little bit more detail. The speed of the ball when it reaches a maximum height, if we think about what's happening here, I'm throwing the ball up, and then the ball will come back down. And at the top here, at the top, at that point, the ball will have a speed of 0. Okay, at the very top, the ball will have a speed of 0. And the reason for that is it's a stationary point. Okay, it's a point where the ball, having gone up and up and up, just pauses for a second before it starts going down again. So we'll have a minute where it's just at a speed of 0. Okay, so at a maximum height, or when it's at rest, the ball will have a speed of 0. To find the time at which it reaches its maximum height, that's going to be our t is equal to 5 down here. And to find that maximum height, then we can take that value for t and sub it into my function. Okay. So just keeping track of everything kind of going on there. So being able to explain what the speed means, okay, in reference to the question, I suppose, being able to explain acceleration, being able to explain why the distance or displacement is acting a particular way or has a particular value, and so on and so forth. So it's just important to have all of that information kind of at the back of your mind as you're doing all of these questions. So if we look now at one of these exam questions, I suppose, so we're starting with one from 2009. Okay, so fairly old exam question here, I suppose. And let's just bear in mind we have displacement, velocity, and acceleration, and we know that to go from one to the other, we would be differentiating here. So given that the object moves in a straight line such that its distance from a fixed point is given by this formula, where s is in meters and t is in seconds, we're asked to find the speed of the object. And we should know that speed is equal to the derivative of displacement. So if I differentiate my displacement, I will get the speed of the object. So let's work out that derivative then. If I'm differentiating this, I need to be careful of the fact that it has a square root, and I need to be careful of to get the derivative of the part under the square root also. So I'm just going to first of all write out the actual function again, and I'm going to use the power of a half there instead of my square root, just so I can keep that kind of clear for myself and remind myself of that part. So differentiating that, I would be multiplying by that power, keeping what's inside the bracket, reduce the power by 1, so we're kind of using a chain rule here, and then multiplying by the part inside the bracket, also the derivative of that part, 2t, giving me an overall answer here of t over t squared plus 1. T over t squared plus 1, the square root of. Then taking that or evaluating that when t is equal to 5. So let's just substitute 5 into my derivative here. So 5 over the square root of 5 squared plus 1, which is 5 over the square root of 26 meters per second. Meters per second. Okay, so fairly straightforward there in terms of answering that question. Kind of with some of these questions, the hard part really can be identifying kind of speed, velocity, acceleration, displacement, all of those parts, and being able to move between them without them telling you exactly what you need to do to move between those. So similarly, if we look here, the distance traveled by an object is given by this function, where s is in meters, t is the time in seconds. We want to find the speed of the object, so we're given displacement to find speed, we just need to differentiate. So let's differentiate the displacement there, and I get 12 minus 4.8t. I want to find that speed after 1.25 seconds. So finding the derivative after 1.25, so 12 minus 4.8 by 1.25, and that's going to give me an overall answer of 6 meters per second, a speed of 6 meters per second. To find how long it takes for the object to stop, so stopping, I'm thinking stationary, I'm thinking speed is equal to 0. I'm thinking speed is equal to 0, so let's set my derivative here equal to 0. So I get 4.8t is equal to 12, and I get t is equal to 12 divided by 4.8, which is going to be 5 over 2, or 2.5. Okay, so we'll go with 5 over 2 seconds. Okay, 5 over 2 seconds there for that last part. Okay, we'll get into a bit of a longer question now, but again, hopefully fairly straightforward. From last year's paper, Fiona is driving on a motorway. She passes a point A on the motorway and her speed is given by this function, where V is her speed in kilometers per hour, t meters after passing the point A. So remember, V here clearly represents velocity because it's with reference to this point A that we have. So it's not just her general speed, it's her speed relative to this point, or after she's passed this point. We want to work out Fiona's speed when she passes the point A. If t is the time in minutes after she passes A, then when she passes the point A, her time would just be 0. So her velocity when t is 0 . Okay, and that's going to give me 109 kilometers per hour. 109 kilometers per hour. There's her speed as she passes A. Okay, again, 1 mark there probably for not having your units in. So always important to include those when we know them, when we can. To work out Fiona's acceleration, and they even give us a little hint here, the rate at which her speed is increasing 5 minutes after she passes the point A, and give your answer in kilometers per hour per minute. So the rate at which her speed is increasing, we're looking for dv dt, the derivative of the velocity function they gave us here. That's going to be 2t squared minus 12t plus 13. We want to evaluate that derivative now when t is 5. So 2 times 5 squared minus 12 times 5 plus 13. So let's work this out. So that's going to be 50 minus 60 plus 13. And that's going to be an answer of 3. Did I do that one out? Right. 12 times 5, 60 plus 13, 50 minus 60 minus 10, 13. Yep, so that's going to give me an answer of 3. It's going to give me a nice answer of 3 there, and that's 3 kilometers per hour per minute. Kilometers per hour per minute. 3 kilometers per hour per minute after 5 minutes. Looking at the next part then, find the time t, so we're looking for t this time, at which she reaches her maximum speed. So maximum speed suggests to me that the derivative will be equal to 0. Second derivative would be less than 0. During the first 4 minutes after she passes the point A, give your answer correct to 2 decimal places. Okay, 2 decimal places is also kind of suggesting little parts to me as well. So let's look at this derivative first of all. So the derivative is 2t squared minus 12t plus 13. And I want that to be equal to 0. Okay, given that I've been told to give my answer correct to 2 decimal places, I'm thinking that I may need to go straight to the quadratic formula because I have a quadratic here. So let's just go straight to that. So t is minus 12 plus or minus 12 squared minus 4 times 2 times 13 all over 2 times 2. So 12 plus or minus 144. And let me see, 4 times 2 times 13 gives me 104 all over 4. So t is 12 plus or minus the square root of 40 over 4. Square root of 40 over 4. So let's just type that one in for ourselves here. So 12 plus root 40 over 4 gives me an answer of 4.58. 4.58. So taking the positive version here, I get an answer of t equals 4.58 hours, I suppose. And then taking the negative option then, so changing my sign here to a negative, I get t is equal to 1.419 hours. Okay, or 1.42, I suppose, if we're matching up to 2 decimal places, as was requested in the question. Okay, so we have 2 answers. We have 4.58 and we have 1.42. And if we're told, I suppose, in this question that we're looking for the maximum speed, we're going to have to use our second derivative to confirm whether these values give me a maximum or a minimum. So getting my second derivative here. I'm going to substitute in both of these points to see what they give me. So 4 by 4.58 minus 12, sorry, 4 by 4.58 minus 12 gives me 6.32, which is greater than 0, which implies that it's a minimum. And subbing in 1.42 in instead of the 4.58 there gives me minus 6.32, which is less than 0, which implies that that is a maximum. Okay, so the time t at which I get a maximum is going to be 1.42 hours. That's my answer there. Okay, looking now at the last part, and I think there was an extra part in the exam question, but I just took it out because it's not one we can fully do yet. But looking at this last little part, we're looking at graphs here. So taking this to be the derivative, of the speed, and obviously v dash dash t to be the second derivative, we're told that at the point 1, the derivative is greater than 0, and at the point 1, the second derivative is less than 0. And we're given these graphs, or these kind of functions or graphs of the original function, vt, the velocity, close to time 1. Okay, so kind of approaching and then following on from. We have to identify which graph it would be that would best represent the velocity at this point. So kind of thinking about what it means for the velocity here. So we're told here that the derivative of the velocity is greater than 0. And we should know derivative of a function means that it's increasing. So the velocity is increasing at point 1. So that means it should be going kind of up the way. And there's two graphs where that's the case. So we have graph B and graph D, where the velocity is increasing. Okay, in the other two sections, we can see the graphs are kind of decreasing at that time, whereas in those two graphs, we can see it is increasing. Now, to decide which is which, we have to look to the second derivative, and the second derivative is the rate of change of the acceleration. Okay, so how is the acceleration changing? So the acceleration is, how is the acceleration changing? And if we think about what it means, the acceleration tells us maybe how the velocity is increasing or decreasing or so on and so forth. And this rate of change then tells us how the acceleration itself is changing and what impact that's going to have on the velocity. We're told here the acceleration, or the rate of change of the acceleration, is actually negative. So what that suggests to me is that the speed is increasing, but the acceleration is decreasing. Okay, so that's just kind of based on what we already know. The derivative of each function tells us whether it's increasing or decreasing. So here the speed is increasing, but the acceleration is decreasing. So what that kind of tells me is that the velocity is increasing at 1, but this increase is slowing. So what I mean by that is the velocity, yes, is increasing at that point, but this increase is decreasing itself. Okay, so if you think about it in terms of, I suppose we're driving a car here, so they are accelerating, but they're kind of stopping accelerating. So they're kind of pulling their foot off the accelerator in a way. So I am still going faster, but I'm not accelerating as quickly. So I'm still kind of increasing, but I'm not increasing as quickly as I was. So what that means for me is it's going to be graph B. If we look at graph B here, the function is increasing, but at point 1, it's starting to kind of taper off a little bit more. It's starting to not be increasing as steeply as it was, whereas graph B is increasing, and at point 1 begins increasing even steadier. Okay, it becomes even steeper. So that tells me that for this question, the graph that best represents the velocity there is graph B. So again, a tricky-ish one maybe to just kind of identify the graphs. They're good to pull in our graphs of derivatives, and even these aren't even graphs of derivatives, but relating what the derivatives mean. So that's kind of why it ties into our rates of change here. So we can see, or we saw, I suppose, in those questions there, one of the key parts of this aspect of this section is really this first box that I have here, displacement, velocity, and acceleration, making sure that you know the difference between each of those and that you'd be able to relate and move between them quite fluently, I suppose, is kind of a key aspect of all these questions.